All right, so here we are. This is our unit on ideas of parallel programming. Now this is going to be a little bit different than some other stuff you guys have seen. If you're in the operating system class, right, we've talked about things like processes, threads, how they go together, right, how they communicate with one another. But what we really haven't talked about is how do you try to actually build software from the ground up that can take advantage of multi-threading, right, having programs broken into pieces that can operate in parallel. That's what we're going to be talking about in this unit. So we've seen things like the syntax for p-threads, right? We know how to create threads, we know how to destroy threads, and we've also seen things, right, like OpenMP, where we can say, okay, hey, for this particular loop, I want it to be, parallelized such that, this part goes to one processor, this other part goes to another processor. We've seen plenty of that. Well, what happens, right, a lot of times, right, is that when people go and try to build software and they try to make it, take advantages of multiple CPUs, right, they try to multi-thread it, it's just kind of done in an ad hoc manner, right? People look at some big program, right? Picture you have a couple hundred line, algorithm, right? Maybe it's all in one method, and they ask themselves, oh, is there anything I can really break out of it? And a lot of times, well, you can maybe do that, right? You can maybe spend days and days poring over your source code, trying to identify kind of what are the independent parts of it. That ends up being a lot of trouble, right? That's actually the reason why a lot of software is, still single thread, right? Because to go from that monolithic block of code to kind of two parallel pieces, right, that could operate at the same time, it's a lot of work, right? Some needs to go through manually, understand how the data relies on data, maybe generated by some other part of the program, right? Or how does the order of execution depend on something else, right? We need to understand a ton of things in order to be able to break something into different pieces. So this is a little bit of an issue. So what we're going to actually look at here, right, is this going to be an idea of how can I structure my programs so it's easy to make them parallel, right? We don't want to do an ad hoc, we want to do it in a structured manner. And if we do it well, right, if we kind of come up with, shall I say, a language, right, of parallel programming, then we'll be able to do things like, well, for one thing, talk about it. Say, okay, I'm going to do this or this, or I'm going to split data up in this sense, right, or divide or distribute data in this way, right? We can have names for things. We'll introduce that in a second. And hopefully, right, what will happen is we'll come up with kind of these standard techniques for how software can be made parallel. And then these standard techniques are going to be things, right, that can be supported by a library, right? So maybe OpenMP, right, can say, okay, hey, they're trying to do a multi-threaded application, right, and they've decided to structure the program in this way. Well, that makes it easier for me to automatically create those threads, format the work, and then combine that back to the results, right? So that would be one thought. All right, so overall what we want, right, is we want just some way to look at software and say, okay, this is how I should think about it if I want to, in the future, make it parallel. All right, so what we're going to do in this particular unit, right, there's really kind of two sides to this. First thing is we're going to talk about patterns in serial programs, right? So we're going to talk a little bit about things like, conditionals, while loops, the sequential operation of source code, right? Kind of how things go line by line. We're going to talk about that, and we're going to say, okay, what are our concerns, right? Or what are our aims if we want to take that piece of code that we've written and make it parallel, right? And so first we're going to start by talking basically about the stuff that might already be out there, right? And kind of challenging some of our assumptions about it. The second thing we're going to do is we're going to describe some general patterns about how code can be structured if we want it to be executed in parallel, right? And we're going to introduce kind of all these different control patterns or data flow patterns, right, of how things can look. So that's going to be kind of our overall goal for this unit. So I've used in here the word pattern, and hopefully you've heard this before. Well, you've heard the idea before. Probably with something called a design pattern. So let me back up and start there. The idea of a design pattern is basically this, well, I like to say it's a common solution to a common problem, right? Most people, when they're kind of going up against something, right, they think to themselves, oh, I have this problem I'm trying to solve. I'm the only one that's ever done this before. Therefore, I'm going to basically just, make it up. I'm going to go from scratch. That's not really true, right? Nobody gets to see an original problem. Well, I mean, maybe some people do, but I mean, on a day-to-day basis, when you look at something, right, you look at a design problem, you need a system to do X, Y, Z, probably someone's already been faced with that problem. So an approach to that is to say, okay, what have people already done? Is there already an existing solution out there, right, that's maybe something that's reusable, right, has, kind of some known, benefits, disadvantages, right, maybe there's some trade-offs, but they can address my scenario, right, my problem. That's called the design pattern, right? This kind of common solution that I can basically take, somebody's description of it and implement it into my software solution and be kind of assured that it's going to act the way I, want it to act, right? It's going to solve my problem. So this is the basic idea of a design pattern, right? We're basically reusing knowledge of somebody else, how they solve some other problem. So what we're going to be talking about in this unit is this idea of structured parallel programming patterns. I know it's a little bit of a mouthful, but the idea, right, is we have patterns of things that say, okay, people are trying to make software parallel. Well, this is how they end up looking, right? They were trying to divide up information, right, so it could be multi-threaded. They ended up doing it like this, right? Those are the type of things we're going to be investigating, right? So a bunch of these different patterns that basically say, how can I structure my data such that it's something that can be easily made parallel? A big advantage to patterns, right, whether they're design patterns, whether they're parallel patterns, is simply having a way to talk about things, right? So when someone's designing a system, they say, oh, hey, this part of the system is, for example, a singleton, right, which is the name of a design pattern. Well, it's a common vocabulary, right? I know what a singleton is, right? You probably know what a singleton is. Somebody else knows what that is as well, right? So all of us will be able to understand how a system goes together just by one word, right? Or I say, oh, it's event-driven, right? Again, we get kind of a bunch of ideas in our head, and it's easier for us to communicate how do different parts of a system go together, right? By understanding kind of what are the common elements of it, right? We have common solutions to common problems. They're going to be in different projects, right? And instead of having to relearn how a project works from scratch, you just say, hey, what design pattern you use? Oh, you use a factory pattern. All of a sudden, you know how their software works, right? This is a very, very important advantage, right? Just having a vocabulary that we can use to describe how things go together. So this is kind of going to be kind of our side benefit, right? In addition to knowing ways to make software parallel, right? We're also going to have ways to discuss with people or to even just search for oh, how do I make this happen, right? How do I make a map or something happen? So what are these patterns going to look like? So I have here the name for a few of them up on the screen. Fork join, map, stencil, reduce, right? So these are names for basically mechanisms by which we can take data, perform some sort of operation on it, and get back some result. Now that probably sounds pretty typical, but the idea here is that these operations are all things that hopefully I can do in parallel, right? There's some sense of independence within them. And if I say something like, oh, I'm going to map this function across this data, what that means is that implies that, I can compute this little piece of data, or I can do some transformation to it independently, right? Map somehow implies that everything is independent. Oh, we'll go into that in more detail. But for now, you can kind of think of that's how it would be used, right? I talk about, oh, I'm going to map it and then reduce it. And maybe you've heard that term, right? Map reduce is basically this systems architecture to basically say, take a bunch of things, split them up, right? Analyze them separately, then combine the result down to a single thing. That's called map reduce, and that's kind of a common method to solve large-scale problems, right? Where you have basically a ton of data, right? Imagine you have some sort of a data analysis problem. You can't compute that all on one machine, right? You need to split it up, analyze it right in parallel across a bunch of machines, and then reduce down that answer to just a single thing. So map reduce is a very common pattern that we see, and we'll see it in terms of map and reduce. We'll look at the different pieces of it. Okay, so for us what we're going to focus on is these different kind of parallel patterns in terms of their concept, right? How does the data flow through them? How does the logic flow through them? We're not going to spend time on a lot of syntax stuff because that depends, right? So based on the different program language you're in, right, based on the different libraries you're going to use, they're all going to have some analog of these features, of these patterns, right? So every kind of parallel threading library should have something that looks like a map, right? Maybe it has a different name, but the functionality will be the same. You're going to have to look up the name, you're going to have to look up the, well, these days actually we do get lucky and sometimes the names are the same. But you're going to have to look up stuff like the syntax, right? What do I pass into that function in order to apply a map? Because that's different for all these different libraries, right? All these different languages, we're not going to really talk about it. We're going to focus instead on the concepts, how I put the concepts together, right? And then when you go to implement something in some programming language, you'll look up and you'll be able to identify what are these concepts, what is the technical stuff that's going to be available there for me to actually do stuff, right? How is that actual feature, how is the reduce actually supported in my language? How does it actually work in OpenMP? So you have to look that up on yourself. There are a bunch of different libraries, right, that can kind of help with multi-threading. I've mentioned OpenMP. Other ones are stuff like, for example, CUDA, Click+, thread building blocks, array building blocks, OpenCL. There's a whole bunch of libraries that do parallel processing or are set up to kind of enable it, right? A lot of things they do is basically just thread management, right? Creating threads, destroying threads, and then kind of have ways, to kind of give these patterns to us, right? Let us say, okay, I want to map across something, right? And then all of a sudden the library takes care of, oh, that means they need to create these threads. That means they need to destroy those threads, right? The library will take care of all that stuff for us behind the scenes. Now, of course, the best choice for us would be simply to go to a programming language which has these patterns built in. So if we were a nice programming language, like for example Lisp, right? Lisp is an awesome programming language. Everything else is just a poor imitation. Lisp, right, has some of these features kind of built in. They have map built in, or they have reduce built in. And it's not so much because they were trying to write software that would be easy to make parallel, it's because that is basically a way to express data transformations in a functional programming language. And we'll talk a little bit more about that in the next section. So before we get into the nitty-gritty of how these things work, I want to introduce two different ways to represent and to understand a program. So typically we're used to a program just being some lines of source code. So you can see there on the top right, we have a little program, void main void, int x equal a, then b on x, right? So we have two functions being called, one of them uses the result from another one. This is how we're used to thinking about programs. Unfortunately, it's a little bit unwieldy and it makes it hard to think about, large programs, right? So if I had, something that was 100 lines, I'd have to constantly be looking, up and down, trying to figure out what goes where, right? Trying to figure out what line relies on what other line. It's just a pain. So there are two other ways, right? We can kind of try to understand source code. And these are the ways that compilers use. So the first is something called a control flow graph. So a control flow graph is a graph that models the flow of control of a program, right? So you have this example, right, of that program. We have that on the left-hand side there, our little grayish boxes, they're A and B, right? What that little picture there is saying is the following. A happens, and then B happens, right? They're in sequence, right? If I had a larger program that had other things like, for example, an if statement or a while loop, I'd have more boxes there, right? And there's little arrows to show, okay, this step goes to this other step, right? It's showing the flow of control. We'll see examples in a little bit that are more interesting, but just think to yourself, it's something basically along the lines of a flow chart, right? It shows your program's kind of overall behavior, right? Does this and this and this, checks this, and based on that, does this or that, right? It shows your overall behavior. For those of you who have been in a class like SER315 or sometimes even SER216, you may have seen this basic idea as something called an activity diagram, right? Which is again a way basically to describe the behavior of a system. Here though, we're just describing the behavior of a piece of code. In addition to this, we have this idea of a data flow graph. So a data flow graph is showing not so much the kind of the sequence in which things are going, right, or the logic behind the scenes. What it's showing is what data depends on what other data, right? So that picture there looks the same. I have A, arrow, and then B. But what that actually means is different than what it meant on the left, right? Instead of meaning that A occurs first and then B occurs, it means that A produces some data that then is used by B, right? So it's showing flow of data. So every edge in a data flow graph is showing data being produced by one step, being consumed by another step. These graphs right here, they look the same, but in general, that's not going to be the case. So you can picture that you have a control flow graph with maybe an if statement in it. Well, it's going to be a little bit bigger. Maybe it has 3 or 4 more nodes here than what I have in the picture. But basically, based on whether that if statement is true or false, the data flow will look different. Right, so if I do true, maybe I do this computation, otherwise else I do this other computation, right? That's affecting how the data is dependent on, other pieces of data in the program, right? And so basically, my data flow graphs, right, those are all they're like snapshots, captures. Maybe I'll use the term trace, right? They're a trace of execution of a program and how the data in its runtime and its execution is related to other data, right? So if that program made different choices, the data it calculated at the end might have been built a different way, right? It might have been built from a different input or something else, right? I don't really know that. All I know is in a data flow graph, it's saying for this kind of program to have run, right, this is how the data in it was related. All right. So these are kind of our first 2 thoughts about new ways we could try and understand our programs. We're going to use this all over the place just to kind of get a sense of when we can make things parallel or when it's a bad idea.